Welcome to the 6th lecture in module 4. In the course on structural health monitoring, we are discussing about the application of structural health monitoring, their design and applications. In this lecture, we will also try to extend the design of SHM concepts through some experimental investigations. We will take up a TLP on the lab scale model. This will be the first of its kind in the lecture series we are going to have in this module. Now, the question comes, what would be the application issues of structural health monitoring design and development when you do it for tension leg platforms on experimental scale. Health monitoring is an important issue when applied to offshore structures. In this lecture, we are going to talk about the health monitoring scheme design, especially for a TLP model on lab scale. Obviously, when TLPs are designed, they never caused failure. We are talking about a post-related failure case in this issue. Post-related failure is a failure created on a lab scale to cause a failure and then assess the failure for its health monitoring. Now, tension leg platform is expressed as TLP. Tension leg platforms are actually one of the kind of offshore platforms which are meant for deep water oil and gas exploration. The moment I say deep waters, the depth of water will exceed about 1200 meters. It can go as high as 1500 meters approximately. We are now talking for a platform which is going to be installed in deep waters. TLP are compliant type offshore structures. I refer you to a spell check on compliancy. So, compliant is not complaint, it is compliant. Compliancy or compliant refers to in general flexibility. Tension leg platforms are structural systems which are very highly flexible. It consists of columns and pontoons as I am drawing on the sketch now here. The mean sea level or still water level is marked horizontal as you see there. It consists of columns and pontoons. I am trying to draw a 3D figure of a rectangular TLP which is now connecting or integrated by different modules of columns and beams. Now, the structure is partially immersed in water, therefore, it raises buoyancy which is an upward force referred as Fb. The platform will also have a weight which is referred as W. W and Fb are essentially coplanar, collinear, and for a symmetric design they are concurrent. We all do agree that TLPs are constructed by steel. Therefore, we knowing the density and the volume of material of column members like I am drawing just now and the pontoon members which are horizontal which I am drawing now on the bottom scale. They are integrally connected and welded together. However, the structure is transparent and hollow in between, wave can pass through the structural system. So, the horizontal members are referred as pontoons and the vertical members are referred as columns. All are hollow steel tubes which are of diameter about 12 to 16 meters. As the wave passes through, the transparency of the system enables flexibility and recentering capability for the platform. The wave can pass through the platform as you see in the picture here. The design concept of TLP is very simple. Buoyancy highly exceeds the weight, therefore, the structure remains afloat. So, that is one of the great advantage of the design. The structure is flexible and remains afloat in water. Now, to hold down this structure into seabed, we need some additional arrangements. These are essentially done by cables or tethers which are anchored to the seabed, that is shown in red color now. So, these tethers are connected from the pontoons and column members to the seabed. They are called as tethers or tendons. Essentially, they are wire like structures which are cables. Now, since buoyancy exceeds the weight by a large value, buoyancy is acting upward, weight is acting downward, the upward force is more, the downward force is lesser. So, the body has a tendency to move up, is it not? Now, I want to bring this body down, I hold this body down by imposing very high pretension. So, all these tendons are pretensioned and therefore, they are called taut mode. The opposite to taut mode is slack mode. Slack mode looks like this. Let us say I have a body, I want to slack moor it, this is what slack mooring is. So, there is no pretension imposed in the body. I have a body, I want to anchor it to the seabed, I want to pull this body down, this is called taut mode. So, they are all taut mode. Now, if I take T0 as initial tension in each tethers or set of tethers, then I can write equation of static equilibrium as W plus 4 T0 is equal to Fp, because W is acting downward, T0 also acts downward, there are 4 because there are 4 legs here, and Fb acts upward. This is my equation of static equilibrium. Now, it is very interesting, the body will be commissioned to the seabed in such a manner that additional weight will be added to the body will further submerge, the tethers will be all stacked and they will be connected to the seabed by some permanent anchoring arrangement. Once the anchoring arrangement is complete, these additional weight will be all removed, the body will have a tendency to move up and that additional weight will be transferred to the tendons in terms of axial tension. Okay, that is how they are commissioned. So, since all the legs are always in tension, this platform is called tension leg platform. Okay. So, this is a typical offshore compliance structure which is useful for deep water oil exploration. There are many advantages of the system. The advantages could be, in case of any lateral load which is hitting the body, only this part of the body is submerged. So, the wave action on the body is minimum, because the deck which is on the place where all operational features are happening, okay, the derrick, the living quarters, etc., all operational features which happen are above water, and there is an enough freeboard which is available for this body. So, that the action of production and drilling is not affected by the splash or by the wave effects on the body, number 1. Number 2, in case of any accidental issues, when these tethers get cut off, let us say they are plugged out because of some accidental conditions, the body will remain afloat and there is no damage to the body as such. Okay, that is an advantage here. So, TLPs are actually recommended for deep waters, and this is what the water depth we are talking about. This water depth is about 1200 to 1500 meters, about 1.5 kilometers. So, now I have a lab scale model of a tension leg platform which has been fabricated to a lab scale, and we are examining the health of this platform under the given wave loads or lateral loads using or causing a postulated failure. That is the whole problem now. So, we have now with us a tension leg platform which is a scaled model which is to be examined on the lab scale. The tension leg platform is commissioned at a specific water depth under deep water condition. It is subjected to lateral loads, that is wave action, and we create a postulated failure. What do you understand by a postulated failure? Postulated failure is a failure created intentionally. So, when you create a failure yourself, you will know the body has already failed. So, we are now examining the health of the structure under this failure condition. So, that has become the structural health monitoring under failed condition using wireless sensor networking. That is the idea what we are going to discuss now in this lecture, where we are going to talk about the lab scale experiment of TLP, the installation of wireless sensor networking, then the data acquisition, and how do we post process the postulated failure data to obtain the health monitoring of the structure. This is a typical wave flume on which the experiment is going to be conducted. You can see here the length of the wave flume is about approximately 100 meters, which is located in Ocean Engineering Department at IIT Madras. It is one of the state of the art facilities which is being located in India, which is housed in our department in the Institute of Technology Madras. So, the model will be installed at a specific test section. This is my test section where the model will be installed. Here the water depth of this is about 4 meters and it is approximately about 60 meters from the wave front, where the wave is generated using servo hydraulic system. As the wave passes the body, the wave is absorbed at the dead end by a wave absorber to avoid any reflection of this wave back to the model. A trolley is being housed, here, so that during examination the body can be investigated for all the measurements on the system. So, the mooring lines are connected at every corner of the deck as you see here, and mooring lines are nothing but the cables or the tethers which are holding down the deck to the seabed by taut mode axial tensile cables. Okay. That is the test setup what we have as far as the wave flume is concerned, which is about 100 meter long. The test section is about 4 meter deep, etc. Okay. The experimental investigations, we are going to use a 4 meter wave flume for the experiment. The primary idea is to investigate the successful application of wireless sensor networking which is going to examine or which is going to be useful in examining the postulated failure of the platform. We are also going to apply the alert monitoring system concept in case a failure is notified. The structural health monitoring system integrated with alert monitoring system should be able to notify the damage and also send SMS, email alert, etc. to the affected or to the client server to indicate the type of damage being caused to the model on the lab scale. That is the whole idea in the design now. Okay. Now, we are integrating the structural health monitoring to alert monitoring system on a lab scale. That is the whole issue we have here. Okay. Now, the typical challenges are choice of the sensor, what type of sensor we should use, then integrated network of the sensors, which we should use for the provided design, and we are proud to declare that the SHM design used in the study is indigenously developed at our lab and it is patented as well. So, it is an indigenous development. So, the objectives behind this design is use commercially available sensors, use existing communication protocol, to develop SHM integrated with alert monitoring system. That is the objective what we are looking for at this moment. So, the experimental setup.